Let's start by opening our custom ERC20 token contract. At the top of the contract, we have the SPDX license identifier, and below that, the version of the Solidity compiler to be used. In order not to code everything from scratch, upgradable versions of some libraries are important. Digital token contract is an upgradable ERC20 token with upgradable ownership directive, and its initialize function can be called only once. The underscore disable initializers function in the constructor method adds another layer of security to that. Note that the constructor method only calls that function. That's the main difference when coding an upgradable contract. You need to change its constructor to a regular function, in this case, the initialize function below. It requires one argument, that is the total number of tokens that will be supplied. And inside this function, the first line is responsible for the constructor method of the ERC20 upgradable token, and its arguments are the name of the token and its symbol. This function is part of the ERC20 upgradable module we imported earlier. The next line sets the owner of this contract, and after that, the last line simply mints the total supply of tokens to the owner of the contract. Now, let's move on to the crowdfunding contract. This contract is also upgradable and uses the same version of Solidity compiler as the token contract. It imports the SafeMath library and the interface for the ERC20 upgradable token. This contract starts by saying that we are going to use the SafeMath operations to the type uint256. Then we declare our state variables. First, we declare a token to be an interface for the type of token we just created. Then we define the states for the crowdfunding functionality such as the campaign goal and the deadline. So we need to keep track of when this contract was originally deployed. The other states will be covered later on. In order for dApps to be able to interact with the contract, events are created and emitted when appropriate. I'll talk more about that when each event is emitted. Once again, as its contract is also upgradable, there is no constructor method, and the initialize function takes its role. It takes as arguments the address of the upgradable token, the campaign goal, and the deadline in seconds, and it sets the corresponding state variables. Note that the initial block time is the time of the deployment of the contract. When calling the pledge function, the caller has to pass in the contribution amount. This function requires some conditions to be met. There are the contribution amount must be a positive number, the campaign mustn't be cancelled, and the deadline mustn't be reached. If all the conditions are met, then the transfer of the tokens from the contributor to this contract can take place. And after a successful transaction, this contract checks if the contributor is a new one. If so, then the total number of contributors is incremented, the contributor's address will be added to the list of unique contributors, and the new user bool is set to true. Otherwise, the new user bool is set to false. Whatever the case, the amount that has just been transferred is added both to the amount contributed by the user and to the total raised by the campaign. After updating the total raised, a check if the campaign goal was reached is performed. If so, an event broadcasting that is emitted. At the end of this function, an event is emitted to broadcast the update on the state of this contract. The next function is a withdraw function that has as its argument the amount to be withdrawn. The contributor can withdraw up to the amount founded by its address. Moreover, the contributors can only withdraw their funds while the campaign goal hasn't been reached. After a successful transfer from this contract to the contributor, the amount contributed is decreased both from the pledger's mapping and from the total raised by the campaign. Then an event is emitted broadcasting the address of the contributor and the amount withdrawn. Next, let's take a look at the function to claim the contributed funds. Only the owner of the campaign can call this function. Another requirement for this function to be executed is that the campaign goal has been reached, now or previously. Of course, the total balance of the contract needs to be a positive number. After claiming, the balance of the contract is reset to zero, and the variable goal was reached is set to true. It may already be true, but it doesn't matter. After that, for dApps, an event is emitted saying that the funds were claimed. The last function is the cancel function. Only the owner can call this function, and the campaign goal mustn't be reached. All the contributors need to be refunded. So for each unique contributor, we need to check how much was transferred to this campaign. First, we need the address of the contributor. The mapping list of users returns the address of each contributor. Then, we feed this address to the pledger's mapping to check the net amount contributed by this address. Having the address of the contributor and the respective amounts contributed it is possible to refund the contributor. After a successful transfer of funds, the amount tracked by the pledger's mapping is set to zero to prevent further transfers. Finally, after all users have been refunded, the campaign is set to be cancelled and an event is emitted.